This video is about error analysis and calculating where the error is and how much of an effect it's going to have. It's also going to help you to identify some of the sources of error. The kind of lab this is going to focus on is one where you have a measured value and a predicted or calculated value, and you're going to compare the two through the error analysis. So let's start with a little experiment. In this experiment, my objective is to determine the acceleration of a car as it races along a track. So I have a car starting from rest. It's going to travel 2 meters and reach at the end of the 2 meters. It'll reach there in half a second. So that's all my data that I'm going to be using. So this is a kinematics problem. And if I look at my givens, I can see that the car starts from rest, it travels 2 meters, and the time is 0.5 seconds. So all the data on my list of givens comes from a measurement in the experiment. So all these variables could have a problem. That's what I want to determine. I need to find the acceleration because that's what the lab asked me to do as the objective. Now, to find the acceleration, I'll use kinematics. So there's my equation. There are my givens with the variables and numbers, numbers and units. Do little calculations, and I calculate, or I predict, that the acceleration is going to be 16 meters per second. In this lab, I'm going to use a separate technique not described in this video for measuring the acceleration. So if I look at this, I can break it up into 3 sections. I've got from the lab's data, all my givens. I've got a calculation that came from the data, and finally I have a second way of measuring. In other words, so this time I'm going to measure the acceleration to be 15.5 meters per second. So that's great. Now look at the percent error. So my percent error is going to be the measured value minus the calculated divided by the calculated. So I've got 15 meters per second minus 16 meters per second divided by 16 meters per second, or 3% error in the lab. So what could have made up this 3% error? So let's take a look at a couple different things. First, I'm going to kind of look at this and change my unknown for the acceleration to be 15.5 meters per second. And now I'm going to look at the effect of the other variables. So what I'm going to do to find my error analysis, I'm going to do some calculations, and I'm going to look at the other variables in the problem, not the acceleration. I'm not going to look at any of the data I calculated earlier. I'm only looking at the things I measured in the experiment. So I measured the initial velocity to be 0, from the way I set it up, the x to be 2 meters, and the time to be 0.5 seconds. And then I calculated, or measured from a separate device, 15.5 meters per second. So the acceleration I'm going to leave alone because that's my objective, and I'm going to look at the other variables that I dealt with. And I'm going to pretend I know everything in that list of givens except one of the original measured variables, that is one of the variables in black. So for this example, let's say that I don't know the distance, and I want to see what distance is necessary to make these other numbers true. So when I look at that, I'll set this up as a kinematics problem again. Kinematics equation, my numbers and units, all in the equation. And I figured out that the distance this thing had to be was 1.9 meters if I'm going to get an acceleration of 15.5 meters per second. So originally I measured 2 meters in my original part of the experiment, first part of the video, and now I'm going backwards and calculating it should have been 1.9 if that acceleration was true. So if I look at that in terms of percent error, measured minus calculated divided by calculated, I get originally in the lab I measured with a meter stick 2 meters, and then I just now calculated 1.9 meters. I'll divide it by 1.9 meters, and that gives me a 5.2% error. So this means that because originally in my lab with a meter stick I measured 2 and I'm calculating 1.9, I had to be off by 10 centimeters. I probably wasn't off by 10 centimeters in my measurement. That's pretty dramatic. The 5.2%, nice number to have, but not really indicative of what's going on with my measurements. So in this section of the error analysis, and every student does their own section and looks at their own variable, it would look like this for my 3 parts. First, I'm going to have some kind of statement. I measure the distance, the measured distance could have been too short because I calculated 1.9, which is shorter than the given 2, by 10 centimeters, or 0.10 meters. Again, that's because my calculations bared that out, which is 5.2%, so that's the error. This is not likely to be my only source of error because I didn't measure it by 10 centimeters. That's huge, and that's not going to happen within, it's a huge error of the sig figs. And then I'll show some calculations about where I came up with that measurement that's different from the other measurement, the original 2 meters. And that's what I showed for my error analysis section. So for the final part of this video, it's your turn. Using the original givens on the left-hand side, ignoring the calculated data, write up 2 more error analysis sections for the initial velocity and t for the data above. In other words, calculate what the initial velocity should have been, something other than 0, and calculate what time should have been, something other than 0.5 seconds, to give me an acceleration of 15.5 meters per second squared.